I'm going to just give a little bit of an introduction to Maplesoft, and particularly about the Engineering Solutions initiative that I'm heading up, and give just to set the scene in terms of the use of our tools for technical solution development. And this then gives a bit of an introduction and leads into our guest here today, Dr. Gudazi, who will talk about the development of suspension design and analysis tools using Maple. We'll pause at the end of his presentation just to put any questions, or if you have any questions, and we can have a discussion, and then we'll wrap up. We expect the whole formal part of the presentation to be around about 50 minutes to allow for time for some discussion. So just to give you a sense of what my group has been actively involved in over the last few years, and in terms of just developing solutions for our clients. And essentially, it's not just about the technology and the tools, and not just about Maple and MapleSim. It's about our expertise, our ability to combine what our capabilities are in terms of tools and expertise to help solve tough engineering problems for our clients. These fall into sort of five basic or to high-level areas. One is just in the terms of providing tools for doing design, validation, and optimization. Specifically for doing sort of early prototyping or virtual prototyping of your designs in order to understand the behaviors of your systems and get a sense of actually if your design is actually going to work. And then the optimization side of it is basically, how can you make that design work better? So we provide tools. We can help to develop tools for our clients to do that. A lot of this is built around our physics-based or physical modeling tools for system-level simulations. And where we are particularly active is in the development of optimized model code for hardware-in-the-loop and software-in-the-loop types of applications. The section we're going to talk about, focus more clearly on today, is on the development of analysis and design calculation tools. And we also provide a lot of help in terms of advanced research, specifically in areas such as model order reduction for model predictive control. So we're going to be talking about the use of specifically Maple for doing analysis and design calculation tools. So if we take a look at how Maple is being used, or in fact we take a look at the whole process for developing technical solutions, there are basically three modes of operation, or three areas where Maple is particularly useful. The first is in the advanced analysis, in the taking first principles, the basic and fundamental relationships, and combining them in some way using our symbolic tools to rapidly arrive at a solution that can then be used to develop some kind of application for deploying or for making that solution available. Typically, the people who are using Maple for doing this kind of work are technical programmers. They're not software developers. They're looking for tools that will allow them to do programming, have a programming language. They can build user interfaces and so forth to then produce a solution that can be used as a calculation tool by people whose fundamental job isn't to do mathematics. It's really just to do supporting calculations in their design work. So by having this design flow, this workflow, we can show that we can take the initial concept for a solution to a particular problem, derive solutions that can then be used in the form of, well, really as an asset of knowledge, that you've developed some knowledge to produce a solution, and then you can use that to produce some kind of CAN solution that can be used further down the chain and into the operations area as a calculation tool. And then what we provide, as you can see from this flow, that Maple supports all the stages in this process. So there are specialized tools, there are tools that are specifically used in different areas in here, but we can show that with Maple you can use this throughout the whole process, and we can provide many features that help to facilitate this whole process. I'm not going to go into a lot of detail here, but just to point out that not only can we facilitate this whole process, but that because we're retaining the mathematical structure throughout the whole process, this really helps to validate the solution. So when somebody asks the question, well, how was this particular solution that's in this calculation tool, how was that developed? We can actually trace that back through the mathematics to the previous stages. And this is a very important aspect of using our tool in this area. And then so we can actually, as you can see, we can from the deployment, from concept to the deployment, Maple really provides the complete environment for technical solution development within any kind of engineering organization. As an example, just to highlight this, this is an example that we introduced some time ago of looking at vehicle dynamics, and we can show that we can use Maple to transcribe the fundamental relationships that come from a schematic or a free body diagram, and then derive the solutions of systems of differential equations for them to be able to then solve it. So this alone brings a huge amount of value to our clients in terms of being able to turn complex physical concepts or fundamental mathematical relationships into these analyses or algorithms. And this is using really the world's most advanced symbolic computing technologies to do this. The important thing, we can do this rapidly and with no errors. Typically, you would be doing this any other way. You would be doing this manually, where obviously it's very slow and very prone to errors. The next step is the development of the technical solution. So, using our comprehensive programming language and advanced numeric solvers, you can develop a solution from a tool that uses the solution that's been developed from that initial work, and then wrap that inside inside a user interface using our interface components. We also provide programming tools that allow you editing tools that allow you to develop the solution very easily. And then finally, you can deploy that calculation tool through various means, either through code generation or through our intranet deployment tool, MapleNet, or our recently released Maple Player, which is free. You can make any of these solutions that you have developed inside of Maple. You can make them freely available within your organization through MapleNet and through the Maple Player. So that really is just to set the scene for why it's important to be considering Maple for developing these kinds of solutions. I'm going to hand over the presentation to Avesta Godazi, who's going to take you through the use of this process and Maple for developing a tool for designing and analysis of vehicle suspensions. So, over to you, Avesta.
Thank you, Paul. Hello, everyone. My today's presentation is about suspension design in Maple, and let me give you some idea about the outline of my presentation. I will have a very short introduction about the application that we have developed and the work that we've done in using Maple for designing suspension system, and then I'll give you a very brief introduction about the suspension system fundamentals, suspension design process, and at last I'll show you how we can use Maple to design suspension system. I will have two examples, a simple one to show the symbolic approach in suspension design, and finally I'll introduce you our developed application, and finally I have a very short conclusion. So as introduction, I can say, as you know, the vehicle ride, handling, and many aspects of vehicle behavior is affected by suspension system. Suspension system is a very important subsystem of vehicles and has very important effect on vehicle behavior. And as you know, the suspension system by itself is a complicated multi-body dynamic system, and to be able to analyze and design such a complicated system, we need a strong mathematical platform. And I believe Maple is a very powerful tool for this purpose, and I'll show you how we use Maple to design a suspension system. But first of all, let's see and review something about suspension system. And the first question is, what is the suspension system? Suspension system easily connects the wheel to the car body, but the connection is not a simple rigid connection. The wheel, a free wheel, has 6 degrees of freedom, but the suspension system reduces it to 3 or 2 degrees of freedom, depends on the types of the wheel. For front wheels, steerable one, it reduces, the degree of freedom of the connected wheel to the body would be 3 vertical movement, rotation about kingpin axis or steering axis, and rotating. And for rear wheels, the wheel just allowed to rotate and has vertical movement without steering. So, what is the function of a suspension system? Suspension system has 3 main functions. Isolation. You know that the road is the source of inducing vibration into the wheel and eventually in the car body, and the suspension system can filter and can isolate these vibrations to provide good ride comfort for the passengers inside of the car. And as well, the other function of the suspension system is for improving the vehicle stability. Again, the wheel alignments, the wheel angles have very important and strong effects on vehicle stability in terms of road, yaw, and other aspects of the vehicle handling. And all of these angles and settings are controlled by suspension system. So again, suspension system is a very important system in stability of the vehicle. And lastly, the road holding is a very the third main function of suspension system. Road holding means we should keep the contact of the wheel and the road effective as much as we can, because having a wheel in contact with the road means we have good traction, good braking, and again, it's a very important aspect of vehicle behavior. So all these functions, isolation, stability, and road holding, are affected by design of a suspension system. And I'll try to show you a suspension system is a very important subsystem in vehicles. So, and now let's take a look on the main parts of a suspension system. It has spring to absorb the energy from the road, shock absorber to dissipate the energy, and mechanism to hold the wheel and connect the wheel to the car body, and bushings for isolating the and absorbing the high frequency content of the vibrations. So the next part of my presentation is about the suspension design process. But before that, let's take a look on the vehicle design roadmap, because the suspension is a part of the vehicle, and the design of a suspension can be understood when we know the vehicle design roadmap. A vehicle design roadmap is formed by 4 main phases. The first phase is pre-design phase. In pre-design phase, we get the main objective of the pre-design phase is marketing research and benchmarking and setting the design goals. And then in the pre-CAD design phase, the second phase, we design the vehicle subsystems, including suspension system, parametrically. I mean, we don't have CAD and geometry, exact geometry in this stage. We just have a very simple geometry, and we should size different subsystem of the vehicle. For example, we should determine the engine power, the stiffness of the suspension, the damping characteristics of the suspension, and after knowing this information, then we can go to the next level and create the CAD data and start to analyze and optimize the system, and go to the last phase to make a prototype and test and have the final design. So currently there are many commercial softwares for analysis and optimization, but for pre-CAD phase, I mean for parametric design and for sizing the subsystems of the vehicle, actually we don't have strong software in the market. But I believe Maple would be, and Maple is a very strong and very good alternative and option for this phase. And our experience show that we can effectively design the suspension system by using Maple, and I'll show you some examples in my presentation. So now let's take a look at the suspension system process specifically. Again, as you can see from the benchmarking phase, we have some data about the existing design, about the vehicle parameter, about the design goals, and based on these inputs, we can have a basic geometry of the suspension system. It's not the exact geometry. We know the mounting point, the hard point, but they are not finalized. It's very rough preliminary geometry. According to this geometry, we can do some suspension mechanism analysis and find the performance curve of suspension in terms of camber by roll, steer by roll, and having these curves, and again by having the vehicle parameters and design goals, we can size the steering, shock absorber, anti-roll bar, and to know the characteristics and stiffness of them. And as well, by knowing all these information, we can do some preliminary vehicle dynamic analysis to be sure that the vehicle is stable and functional. And after doing this pre-design or preliminary design process, we can go to the next level and start to analyze and optimize the system based on the system geometry. And again, then we can go to the prototyping and testing phase, and finally we will have the final design. So now I want to show you 2 examples of how my team used Maple to design a suspension system. The first one is a relatively simple one. You can see the formulation and equations, and I'll show you how the symbolic approach would be beneficial in designing of suspension system. And finally, I'll show you our developed application, and I give you some idea about how you can use it. So let me go to Maple. Okay, this is the first one, suspension design example. All the equation can be seen in this example, and you can see how we develop a very, not very, it's a relatively simple, simple example, but it can be used for designing of suspension system. So as it's the worksheet show that we start with calculation of the effective mass of each wheel based on the vehicle mass and the position of the center of gravity of the vehicle, and after calculating the effective mass of each wheel, then we can go to the next level, and by using a quarter car model, then, and by having the magic number for the frequency, natural frequency of the front suspension, we can size the spring stiffness. But the question is, what is the magic number? I can give you a number for the suspension system. Typically, for the front suspension system, 1 hertz is a good number for the natural frequency of the front suspension. And after calculating the theoretical stiffness of the suspension system, as you know, this theoretical stiffness is formed based on this assumption that the spring is located in the center of the wheel, as you can see in this picture. But it's not a physical assumption, and in reality, spring is located elsewhere. And so we should correct the spring stiffness based on the installation position of the spring. And for this, we define the installation factor. As you can see here, this is the spring or damper movement to the wheel movement. And by using this factor, we can have the final stiffness of the suspension system. Again, we can repeat this process for the rear suspension, but the only difference is the rear suspension magic number for natural frequency, it's not 1 hertz, it's supposed to be 1.2 hertz. And again, we can change this theoretical stiffness to actual stiffness by using the installation factor. And in the next level, we try to find the damping coefficient of this shock absorber for the front and rear suspension. And again, we need a magic number for damping ratio, and I can suggest you to use a number between 0.3 to 0.6, depends on the types of the suspension vehicle. And again, we have installation factor again for spring and for shock absorbers, and in final stage, we try to size the anti-roll bar by using this simple roll model, 1 degree of freedom vehicle roll model, as you can see here. And again, we calculate the torsional stiffness of the suspension system due to the torsional stiffness that is generated by springs. And then again, we need the other magic number, the roll gain. Roll gain is the allowable roll angle for 1 G lateral acceleration. And again, I can give you the approximation for this number is about 4 to 8 degree per G, GR in this formulation. And by having this, I can calculate the whole torsional stiffness that we need, and a part of this torsional stiffness is provided by springs, and the remaining part should be provided by front and rear anti-roll bars, as you can see in this calculation. And in the last stage, I can put the number, substitute the number into the symbolic equations, and plot the curves and see, for example, the effect of mass on the effect of vehicle mass on the front suspension stiffness and for the other parts of the system. And this is the benefit of symbolic approach, because now I can do sensitivity analysis and optimization very easy. So, and then the next Maple application that I would like to introduce you in this presentation is a little bit sophisticated one. This is the suspension design toolbox that I and my student has worked on it for a few months, and this is a very This suspension design toolbox is formed based on a very popular configuration of suspension systems in the cars, MacPherson suspension for the front and torsion beam for the rear, but we can develop the other types, for example, for multi-links or double wishbones. So here you can see we have a list for vehicle data. You can enter all data here, and then this part is dedicated to magic numbers. We can put all magic numbers here, and in this part we can introduce all the geometry of the different points of front suspension system in this forms, in this list. And again, for the rear suspension system, we can introduce the dimension of their and put them in this fields, as you can see. And then we can run the simulation. It start to work. And after a while, the simulation and analysis would be completed, and I'll show you the results of this code. This code is the object-oriented one. It's and the previous one. In the previous one, you can see all the equations, but in this one, all the equations are embedded. So in the next part of the application, you can see the result of a kinematic analysis. We have many. Sorry, it is still running. Yep. So we have different performance curves. For example, you can have camber by bump. You can plot it, and you can see the linearized factors, which is very useful in vehicle dynamic analysis for camber by bump factor here. And again, you can, for example, have spring deflection, damper deflection, spring installation factor, damper installation factor, camber by roll, scrap by roll, roll center position in vertical and horizontal deflection. Many other performance curve suspension system we can have, and in each case you can plot for example, in this plot show the spring installation factor, and as well we can have the linearized number. And for the rear suspension as well, I can have all performance curve of the suspension system for the torsion beam suspension. And in addition to the performance curve of the suspension system, I can have the geometry of the wheel in terms of inclination angle, caster angle, scrap radius, caster offset, and the other important dimensions that we can use them for steering system design. And finally, we have the stiffness and damping of the system from the front and rear suspension, and we have front suspension spring rate, rear suspension spring rate, shock absorbers rate for the front and rear, anti-roll bar for front, and torsion beam stiffness for the rear. And the bottom of the application, we have a very short terminology for who that they are not familiar with terms like camber by roll or other vehicle dynamic terms. And so lastly, as a conclusion, I can say during the pre-CAD phase of vehicle design, we need a strong mathematical platform for parametric design of the systems. And suspension system is just example. We need such a mathematical tools for other part of the system. For example, we can use this approach to calculate the power of the engine, for calculating the ratio of the transmission, for ratio of the differentials, and many other things. And according to our experiences in industry and in university, we believe maple can be a very good mathematical tools for doing such a task. And hopefully we continue our work on maple and using maple in other different application in designing and developing vehicle subsystems. Thank you, and please I ask Paul to continue the webinar.
Okay. Okay, in which case I'll just wrap up by pointing out that the application that Dr. Ghazazi presented today is available on the Maple Application Center. Just need to register for the App Center to be able to download it. If you have Maple, great, but if you don't, you can try the Maple Player. This allows you to interact with the tool as shown in this presentation. Obviously, you can't make any changes to it, and certainly if you wanted to get into more detail, then we would certainly recommend that you request an evaluation of the of Maple to, or even discuss with us how you would like to take this process further forward. So I just wanted to wrap up by just talking a little bit about, obviously this is the start of the process, and certainly once you have done the design work, it's a very good idea to be able to at least get some sense of how those parameters are going to behave in some kind of virtual prototype of the vehicle model. And this is really where MapleSim comes into play. So we can provide MapleSim as an environment for you to take the design parameters and then take the whole suspension through its exercises. So this is one extreme example of taking it off-road. We can also take a look at how the vehicle would behave in a steering maneuver, and then or even just take it through some kind of KNC test, virtual KNC test on a virtual shaker table. But again, you get a lot of insight, very early insight, into how the vehicle or the proposed design will actually behave under some real-world conditions. So with that, I'd just like to wrap up and thank Dr. Ghazazi for his great presentation. I'm sure you'll agree that it looks like a powerful and easy-to-use range of design tools for the vehicle suspension design and virtual prototyping once you bring it into the MapleSim environment. And really, my part of this presentation is just to make sure that you understand that Maple is not just about mathematics, it's not just about symbolics, it's a tool that provides you an end-to-end solution development from the concepts of the solution right through to the deployment of the solution throughout your organization. And then finally, just to reiterate that Maplesoft Engineering Solutions is here to provide tools and expertise to maximize your return investment by combining professional services with our products that allow you to reduce development risk, produce better products, and get to market faster, quicker.